Mark time, 2 minutes.
Det ser ut som det är live. Det ser jättearg ut på bild. Jo, så det är nog live. Det ser inte arg ut.
Det ska verkligen stå live. Ser du en länk det står live på?
Nu ska vi säga att du tog i presentation.
Jag kör dubbla livestreams från min internetuppkoppling, så det kan vara att det bara kopplar ner igen. Nu är det 3 stycken.
Det var ju där också. Det var inte så bra.
Men det där, om chatten inte funkar, då kan jag inte använda YouTube. Jag är lite orolig över den delen.
Jag kunde ju helst sätta in hörlurarna igen sen för dubbelcyklar. Jag kunde ju alldeles nyss kunna skriva på den andra grejen. Men jag kan inte skriva på live-grejen nu. Men den andra live-grejen som jag är klar med, den kunde jag skriva på. Nej,
det förstår jag. Men vad kommer du inte åt chatten, eller säger han att du inte får skriva? Vad händer?
Jag kan visa.
Hur ser det ut upp till höger? Upp. Gött. All right. Men då tror jag...
Men då kan jag skicka, men jag kan inte se att jag har skickat. Jag kan inte se vad någon annan skrivit.
Kan du filma upp till höger på skärmen? För på min skärm som inte är ansluten, då står det, ja exakt, så finns det med att du har skrivit i alla fall.
Men jag har nästan aldrig skrivit någonting på YouTube, så det är möjligt att jag bara missat någonting liksom.
Är den inställd på toppchatt eller på livechatt? Längst upp på chattrutan.
Ja, det står väl varken eller. Man kan dölja chatten, det är det jag kan se att man kan göra.
Kan du filma upp på chattrutan?
Men det ser ju ut som om det är någonting som nästan saknas där i den här rutan liksom. Så man skulle kunna dra upp och ner grejer där egentligen.
Går det att scrolla upp där?
Det funkar ju.
Gött.
Smart.
Nej, men då funkar det i alla fall då. Right. Men jag kör igenom presentationen, så får du väl skriva i chatten eller liknande vad du tycker. Jag kommer köra på bara, så kan vi ta det efteråt om du har inputs, du vill säga i person. All right. Men jag avslutar den här videoströmmen och fortsätter på de andra 2. Det är förvirrande många ansikten av mig själv.
Det är så mycket gladare ut i den här än vad jag gör på den andra. Det är konstigt. Det kanske är för att den är senare. Ja, nu ser vi gladare ut.
Yes. Videon är med lagg. Du ser om jag gör sådär.
Ja, men då stänger vi av här och så lyssnar jag bara.
Yes. Tjo. Hi, welcome everybody to my thesis presentation. In this presentation, I will try to summarize the work I've been doing as a part of my PhD for the last 4 to 5 years. And I've decided to split the presentation up into 4 distinct parts, starting with an introduction to batteries and then sodium-ion batteries. Then we'll move on to SAI and anodes, which is the work in papers 1, 2, and 3. After that, we'll have a look at cathodes and the synthesis of Prussian white cathodes more specifically, which was performed as a part of paper 4. And last but not least, we'll look into some electrolyte screening and into some non-flammable electrolytes, which was the focus of papers 5, 6, and 7. All right, so if we start from the real beginning, what is a battery? Well, a battery is an energy storage and conversion device. It takes electrical energy, converts it to chemical energy, and stores it. And it can also do the opposite to release electrical energy. Now, there are many types of battery chemistries, and the most famous nowadays is lithium-ion batteries. And they come in all shapes and sizes, from really small batteries to really big batteries. But no matter the battery chemistry, we kind of want the same things from all batteries. We want them to store as much energy as possible. We want them to charge and discharge as fast as possible. That means a high power density. And we also want them to last as long as possible. So we want them durable. We want them to live for a long time and manage a lot of cycles before they deteriorate. Furthermore, we want them very safe as possible, and we want them to cost as little as possible. Now, depending on your application, these parameters become more or less prioritized. For example, the mobile phone you see to the top right, that's a battery that is very sensitive to volumetric energy density, but not as sensitive to price, because the mobile phone costs a lot and you will only use it for 3 years. But it's worth spending the money on the battery. If we move up to bigger batteries like electric car batteries, then safety becomes very important, and also the durability, which should extend for perhaps 10 years. And at this point, the price becomes more important as well, since it constitutes a big part of the car price. If we go even further up in scale to grid storage applications, you see a shipping container filled with batteries, then it's actually cost that becomes the most important factor. Of course, the other parameters will be important because they affect the cost, but kilowatt hour per dollar is the primary focus of the really large scale batteries. Now, I talked a bit about lithium-ion batteries, but sodium-ion batteries are very close to lithium-ion batteries. So when I present this schematic of how a battery works, it's basically true for both cell types. There are principally 4 components in a battery, starting with the current collectors, which move the electrons to the external circuit of the battery, and then the electrodes. There are 2 electrodes, one anode, one cathode, one being the negative electrode and one being the positive. These electrodes themselves consist of 3 different types of materials. We have the binder, we have the active material, and we have the conductive additive. And it's actually the active material that is the heart of the battery, which actually stores our chemical energy. The last 2 components are supporting components. We have the electrolyte, which is the medium that enables sodium ions to move from one electrode to the other. And since this is a liquid part, especially in the work I've been doing, we need a separator, which prevents the electrodes from coming together. The electrolyte is composed of a solvent and a salt, and the separator is composed of a permeable membrane, which allows liquids through it, but it stops electrons from contacting. So it's an electrical insulator. Now, having looked at batteries in general, I want to focus a bit on sodium-ion batteries and why sodium-ion batteries are worth researching. And I'm going to do this by comparing them to lithium-ion batteries, because that's the closest cell type to sodium-ion batteries. The first argument for sodium is, of course, the abundance of sodium. Sodium exists in 2.6% of the upper Earth's crust. while the equivalent number for lithium is 22 ppm. And on top of this, sodium is equally distributed around the globe. So there is no country that has low access to sodium. You can get it everywhere within any border of any country, while lithium is concentrated in a few parts of the world. Now, sodium sounds really good, but there's some drawbacks as well. And there's a reason why we started with lithium-ion batteries. For one, lithium has a lower reduction potential, above 0.3 volts. So this means that you will probably get higher voltage from a lithium battery than a sodium battery. But this is not a huge factor because the voltage of a battery actually varies more between different lithium-ion battery chemistries than 0.3 volts. However, one important thing is the larger ionic radii of sodium as compared to lithium, because this makes a lot of trouble in the cell. It's more difficult to find suitable electrode materials. You will have higher chances to get trouble with volume expansion and such, and it would usually also limit the capacity of your electrode materials as compared to lithium. And from my perspective, these pros and cons are actually a bit superficial, because when you look at a lithium-ion battery, a very small percent of the cost is actually the cost of lithium. So even though sodium is much cheaper than lithium, it's not the cost driver in a battery. So in order to really make a good case for sodium-ion batteries, we have to look at what is the actual cost in a battery. Well, in lithium-ion batteries, it's the cost of cobalt, nickel, copper, and manganese, but mostly the three first ones. So if we want to build a cheap battery, we cannot just substitute lithium for sodium and think we're saving money. We have to also substitute other materials. One additional advantage of sodium is that it is compatible with aluminium on the anode side current collector, which means we don't have to use copper foils. This saves money and it saves weight. However, we really need to substitute the transition metals like cobalt to something like iron for sodium-ion batteries to make economical sense. And therefore, I have directed a lot of effort in the latter part of this thesis to build batteries which only consist of sodium, iron, and aluminium, with some extra components made from carbon and nitrogen. So before we jump into the actual papers, I want to talk about the anodes and the SAI, because the first three papers are dealing with the SAI. SAI stands for solid electrolyte interface, and it's actually a passivation layer that forms on the anode. And this is because we want high voltage batteries, which means we want anodes with a really low potential, so we can match it versus a high potential cathode. But in doing this, we actually go beyond the electrolyte stability window, which means we are reducing the electrolyte on the anode. Now, this formation of a surface film that stops the decomposition of the electrolyte was what made lithium-ion batteries possible. And sodium is no different in this regard. And what makes a SAI layer functional and good to have in your battery is basically three properties. The first one being that it's blocking electrons, because that's what stops the reaction from just continuing ad infinitum. Secondly, the SAI layer must allow sodium ions to move in and out of the anode, so it must be ionically conductive. And thirdly, and this is very important, it should be non-soluble and chemically inert. This is because we only want to form the SAI once, because we consume the components of the battery as we form it. And every time we form an SAI layer, we lower our capacity and our energy density, and we also form gases in the battery. So we want to form it quickly and only once, and then it should act like a passive component. And this is the first thing I looked at in paper 1, where I tested the static stability of sodium SAI compared to lithium SAI. And I did this in standard carbonate electrolytes. Now, we found that the sodium SAI has a much higher self-discharge, which means that when you fully sodiate carbon, it will start climbing in potential spontaneously much quicker than the equivalent lithium cell would. So I tested 2 different lithium systems and 3 different sodium systems to see what effects were occurring in such cells. What we found was basically that pure sodium-ion batteries without any additives has horrendous self-discharge. We saw that lithium performs much better, and we saw that it's not the potential difference between sodium and lithium that made a difference. One of the best systems was lithium that was kept at the sodium-ion potential. We also saw that surface area and additives can make a huge difference in this self-discharge behavior. And I also used X-ray photoelectron spectroscopy to show that the SAI is actually shrinking during pauses. Now this is quite important because that means that it's not an SAI that continuously grows that is the effect. The shrinking part actually indicates that the SAI is going into solution. And this is probably, if you read in literature, people say that sodium salts are more soluble than lithium salts. This is true in water at least, and it seems to be true in carbonates as well, because we're losing the SAI and we have to reform it. But I wanted to see more applied systems. So in paper 2, I synthesized tin phosphide, which is a quite interesting anode material. It has a high capacity, it has a good voltage, but it has some complex behavior. For example, when you discharge it the first time, when you sodiate it, it gets reduced to metallic tin and elemental phosphorus. I proved this by doing powder XRD and operand XRD. And you can see in the picture to your upper left, the characteristic peaks of tin phosphide disappearing during the first discharge, and they do not reappear as we charge or dissociate the cell. Now, this material had been used a lot in literature, and they all show the same things. A couple of tens of cycles where it cycled really well, and then an abrupt decline of capacity. So in paper 2, we studied the SAI again using XPS. The strategy was to take several sample points at different stages of cycling during the first 1.5 cycles. And the results showed that the SAI is actually formed very thick, and then it grows thin during dissociation, and then again grows thick as we sodiate. We could also show a wide variance of composition during this charge and discharge cycling, which means that the SAI is not stable. This alone wouldn't explain why we lose so much capacity after 50 cycles, because we had so much electrolyte in these cells that it shouldn't have made such a difference. So we decided to work further, and in paper 3, I decided to test 2 different salts, but also test 2 different cycling regimes. One regime where we charge to 2.5 volts, and one where we discharge or charge to 1.2 volts. The reasoning here is that all of the useful electrochemistry in tin phosphide occurs under 1 volt. So we really shouldn't change the capacity that much by lowering the charge cutoff. But when we got the results, we saw that a lower charge cutoff voltage actually stabilized the cells a lot using both salts. Now, sodium PF6 was always underperforming compared to sodium FSI, but actually the charge cutoff voltage made a bigger difference. Now, this had been tested in tin systems before, but we could show with XPS that the additional charge potential actually stripped the SAI of tin particles. And since alloy electrodes usually suffer from capacity degradation via agglomeration of small particles, we could show that if you charge your cell too high, your tin particles will become clean, touch each other, and fuse together. So this is the main point of paper 3, and with that we'll move to cathodes in paper 4. Excuse me. Now, paper 4 deals with a cathode material, Prussian white, and it does look at this material from a synthesis and characterization point of view. But I want to tell you why it's interesting to look at this material. And the first thing is the composition. It's composition is sodium, iron, carbon, and nitrogen. Very green, very cheap. It has a really good theoretical capacity at 117 milliamps per gram and a decent voltage of 3.1 volts. So this is a really good match for sodium-ion batteries, but it is a complex. It's actually a coordination complex that has an adaptable framework. It has defects during synthesis. It can shift crystallographic phases depending on water content and sodium content. So a lot of this work was iterative study of the effect of different parameters on the final outcome of the cell. That included Oranda XRD, morphology studies, TGA to characterize the water content, and of course cycling to see how good was the material as a battery material. My purpose to participate in this study was quite selfish because I wanted Prussian white cathode material to test other things in a sodium cell. And to do that, I actually had to scale up the production at the same time because I wanted to build a lot of batteries with a lot of electrodes. So I scaled up this synthesis in several different steps from really small until quite large synthesis. So having procured a good cathode material, I moved on to paper 5, where I wanted to study electrolytes. Electrolytes are a real Achilles heel in sodium-ion batteries, which means it's really difficult to study anodes or cathodes because your electrolyte is so poor that you don't know what is being troublesome in the cell. It could be your electrolyte misbehaving just as well as your cathode material. And since I only knew from papers 1, 2, and 3 that carbonates were not a magic answer to this problem, I tested a lot of different electrolytes. I characterized ionic conductivity with salt concentration. I did electrochemical stability tests using cyclic voltammetry. And I tested full cells. And this is a big difference compared to the literature that was out a couple of years ago. It's not until you truly remove the sodium metal out of the cell, it becomes a sodium ion battery. And I found that if you remove the sodium metal, most of the electrolytes that were dysfunctional in contact with sodium metal actually worked rather well in sodium ion full cells. We got good results here. 11 out of 13 could cycle, but we picked 5 solvents for additive studies, and we picked about 7 compositions of solvent mixtures to study further. So by combining these solvents with additives and also combining solvents together, we built up a matrix of about 47, 48 samples, which actually was quite a lot to test. So we did a standardized matrix of testing, including 3 electrode cells measurements, ICI, which is a current interruption technique, which can measure the resistance of both electrodes. And we could describe the effect of additives on several different solvent classes and also find really good electrolyte candidates. Some of the candidates didn't make it into paper 5 because they were too interesting and deserved further studies. And that brings us to paper 6. Paper 6 and 7 looks at non-flammable electrolytes, and the basis for this is that we found that a salt called NaBOB actually dissolved well in a solvent called TMP, trimethyl phosphate. Now, to put this briefly, TMP is a non-flammable solvent. In fact, it's used as a flame retardant, but it doesn't work versus carbonaceous anodes without high salt concentrations. And for NaBOB, it's an interesting salt because its lithium cousin LiBoB or LiBoB is an excellent film former, but sodium BOB had never been cycled because no one knew of any solvent that could dissolve great enough amounts for it to be useful. But since we found that NaBOB dissolved in TMP, we could actually construct a non-flammable electrolyte using sodium BOB. And we wanted to test the stability of this salt. So we synthesized and characterized the salt. I tested half cells. The initial tries were somewhat promising. You can see that sodium BOB with TMP has excellent capacity retention, but very high polarization, while the standard sodium PF6 has low polarization, but capacity degradation. Furthermore, the ionic conductivity tests show that we had ionic conductivity very close to the sodium hexafluorophosphate salt. So not the best, but definitely good enough. And if we move on to the full cell testing, we can see as expected that TMP does not work well with hard carbon anodes. Not when you're using the traditional salt, but when you add this new NaBOB, you actually get much better cycling behavior. We could prove that from cyclic voltammetry that sodium BOB breaks down long before the TMP does, and that forms an SAI based on the salt, which is quite functional. We can also, of course, see that here in the galvanostatic curve, where we have an extra plateau from the decomposition of NaBOB. Now, this is very promising, but it's not by far close to what an application would need. So we decided to test some additives as well. So I added different amounts of vinylene carbonate additive to these cells, both the sodium PF6 and the NaBOB. And it did improve both cells, both electrolytes, quite dramatically. Even though it improved BOB, it didn't improve BOB as much as it did improve sodium PF6. And we can see that from the zoom in here, that when we add vinyl VC, vinyl carbonate, to the electrolyte, it breaks down long before TMP, just as BOB does, but it forms an SAI that is very good in sodium PF6. For BOB, it seems like VC and BOB breaks down at the same time, which meant that we needed a lot of VC to really get a good effect. And unfortunately, this meant that we could induce instability in the system by having too much VC in there. Now, during paper 5, we also found another solvent, namely N-methylpyrrolidone, NMP, a very famous solvent in the battery industry. NMP could dissolve BOB even more than TMP, but NMP is flammable and toxic. So we wanted to see if we could make a binary solvent where we could reduce the amount of NMP but preserve the ionic conductivity. I tested mixtures based on different solvent compositions and measured ionic conductivity based on the weight percent. And you can see that pure NMP has a really high ionic conductivity. However, since we wanted a non-flammable electrolyte, we did flammability tests, and those tests showed that you needed at least 40 volume percent TMP to keep your electrolyte non-flammable. But at 40% TMP, we still had a good conductivity, better than sodium PF6 in TMP. We also found that mixing these solvents brought the freezing point really low, and we had 1 millisiemens of conductivity, even down at -30. So the physical properties of these mixtures were really good, but the cycling was not as convincing. Basically, you can see here that from TMP to 50-50 mixtures and pure NMP, it only gets worse. So we're not improving cycling by mixing these solvents. And if we compare to a reference of carbonates, ECDC, with 1 molar sodium PF6, you can see that the reference is much better in the first 5 cycles. However, we were positively surprised when we looked at the long-term cycling, because within 100 cycles, our mixtures and our pure TMP actually starts beating the reference, preserving more capacity and having a higher coulombic efficiency than the state-of-the-art electrolytes. Now, we should add additives to this system as well, but there wasn't time for it. But it's worthwhile exploring. And I should also comment that even though NMP is not our dream solvent because it's flammable and toxic, it did show a really good cycling performance at high temperature. So that's basically the main point of paper 7. So let's go through again, and I'll give some conclusions. In paper 1, we saw that the SI in sodium-ion batteries was inferior to lithium-ion batteries, especially in carbonate solvents. In papers 2 and 3, I described the SI behavior on tin phosphide anodes and suggested a possible degradation mechanism with agglomeration of tin particles. In paper 4, we showed a pathway to synthesizing fully sodiated Prussian white with low defect concentration in ambient pressure and low temperature synthesis. In paper 5, I gave an overview of several different solvent classes and their interaction with both additives and their performance in binary solvent mixtures. While in papers 6 and 7, I show some new ways to get a non-flammable electrolytes without using highly fluorinated solvents or high concentrations of salts. So that's about it for this presentation, and I would like to conclude by thanking all the generous funding I've gotten from different agencies. I would also, of course, like to thank all my co-authors and my wonderful colleagues. I would like to thank Christina Edström, who's the head of the Ångström Advanced Battery Center, who built the wonderful group I've been working in, and also Daniel Brandell, my second supervisor, who really introduced me to batteries. But most of all, I would like to thank my main supervisor, Jesse Ronnieskeet, who has supported and helped me through all my PhD studies, and I couldn't have done this without his help. So that's it for me. I thank you